So the intros section here, section 2.1, is just going to talk a little bit about where we're going to use some of this stuff, where you could see it, and that's a good question. So what I did to kind of make this a little bit more personal to us here in Michigan is I looked at some of the recent COVID data. So this is from March 1st through April 20th. And this is the number of new cases per day. You can see how things have fluctuated a lot. Kind of curious that this curve just kind of jumped up here. This is the 7-day moving average, which has a little bit less noise in it than maybe another, or the actual daily amounts. So let's fit a curve to this. And that's my curve. Now let me shut off the data. And what I want to do is I want to kind of analyze this curve and understand how things are changing. And that's actually the first part of your class here, is understanding how things change. Now, to figure out how things are changing, that is, the rate of cases is changing, one way you could do things is you could just pick a couple cases. So here's a couple pieces of our data point. So I got one a while ago and one more recently, and we can fit a line between those two curves. Okay, great. Now that line shows you, on average, how things are changing. So yeah, you're getting, a change that if you actually calculated the exact numbers would be a little bit more than 50 cases a day increase in the rate over time. But like I said, that's an average. That's how it's changing between those 2 points. Now, is it changing that way throughout the interval? Well, no, actually it's not. It starts out increasing kind of slowly, but then what happens when you get closer and closer to this endpoint? The rate of change is going up faster, right? So, So this average rate of change here, well, it's okay, but a lot of times you want to know how things are changing, not on average, but at an instant, right now. If you were on the freeway and traveling up to Mackinac, the cop pulls you over and says, hey, I clocked you doing 80. You say, oh, but my average speed is 65. Does he care? No. He cares about your speed at the instant he shot you with his radar gun. All right? How you're changing at that instant. So how are we going to come around to changing this to figure out, well, how is the function changing at an instant? So let me put up a different little graph here, this one. And the idea that you could come up with is, well, instead of looking at this interval for such a large gap, how about if we put those dates closer? So maybe I'll slide this in a little bit. So now I'm getting the average rate of change. It's just not over as big of a time interval. So this is probably a better representation of what's happening on average or at an instant. And then I can keep going, right? I can make it closer and closer and closer. And finally, I can get really, really close to within 1/100th. So, wow, that's really, really close. And this average rate of change is taking place over such a short time interval that it's almost like the instantaneous rate of change. Now, the instantaneous rate of change is where we're headed initially in this course. It's something called the derivative. In fact, for your derivative notation, you've got to write down here. This is going to tell you how a function is changing at an instant. And that's what separates it from algebra. In your algebra courses, you looked at this stuff, how things are changing on average. Now we can look at things and find out how things are changing at an instant. If you take a look at the slope of this line here, our little approximation, it's about 112.18. If you were actually able to calculate the exact value, if you knew the calculus behind this, then the exact answer we should get would be 112.23. So pretty close. So our idea of an approximation actually works pretty good. Now that's the first roughly half of this course, maybe even 2/3, is working with the derivative and understanding its applications, rates of change, etc. But then we're going to do the opposite of the derivative, the opposite process. And what's the opposite process going to be? Well, let me shut off a couple of these things. And let's see, that's the other one there. The opposite would be to accumulate things and to find areas. Now, if you were looking at other applications, maybe you had some curve representing your speed or your rate of change, then the area underneath this curve would be how far you travel. In this case, this is the rate of change of the number of cases we have. But if you found the area underneath this curve, that would tell you the number of cases, the total number of cases up to that point. Now, is there a formula for this? Is there, a nice, neat, like we can do it with rectangles or triangles? Well, not really. They don't fit underneath here too well, do they? This is just a crazy curve. In fact, if you looked at it as a fourth degree curve with some really wild coefficients. So, yeah, pretty ugly there. In any case, we can find the area underneath here, and that's what the opposite of the derivative is going to do. It's going to allow us to calculate that area. So, pretty cool. And that total area here turns out to be a little over 50,000 cases in that interval, and that's actually pretty close to the real total. I don't remember exactly off the top of my head what that was, but it's reasonably close. But that's going to be the second part or major part of this class, is trying to figure out what the area is underneath that curve. So in a rough sense, that's where we're going with the first semester of calculus. And then beyond that, there's some more applications that you're going to get into, and then Calc 2 takes it even farther and farther. So in short, this modern world just really wouldn't exist without calculus. There's so many things that you depend on, from GPS to MRIs to your car, bridges, dams. There's just so much of our world that we simply wouldn't have were it not for calculus. So it's a cool subject. I'll talk a little bit more about the history, section 2.4. But for now, any questions or thoughts on the little demo here? All right. So we'll call that a wrap and move on to section 2.